act as given this K. And this has natural vertex algebra structure. And this is called the universal affine vertex algebra. And this is you can think this as a version of enveloping algebra for G hat, in the sense that the G hat module about this vertex algebra is the same as a smooth G hat module of level K. So as long as you, in particular, as long as you consider the category of highest order representation, the representation of the same. And in this case, the diagram becomes like this. So you start with this vertex operator algebra. The corresponding algebra is just enveloping algebra G. So this corresponds to the fact that G hat is affinization of G. And of course, the corresponding classical object is a polynomial function on G hat with natural Poisson structure. And the Poisson vertex algebra is the arc space of G star. So I will not talk about very much. And in this case, it's really a commutative diagram. So in particular, associate variety for this vertex algebra is a function, dual of G. And you can also talk about a similar diagram for modules. So if you consider the VOA module, corresponding object here, the natural one is a bimodule. And you get the Poisson module, and here Poisson module. So if you apply this diagram to here, so if, for example, if you consider the category of Kazan-Lustig category, which is a parabolic subcategory of highest category of G hat, which are locally finite over GT. What you get here is Harshchandra, the category of Harshchandra bimodule. And here, quasi-coherent shifts on G star and corresponding jet objects here. So if you have something here or here, you want to try to upgrade to the setting of vertex algebras. Now, so this case, but this case is nice, but we are more interested in the simple quotient of this affine vertex algebra. So this is the same notation as this row. This is a simple quotient of this universal affine vertex algebra as a G hat module. And this has a natural structure of a quotient vertex algebra. And as this row explained, the category of this module is a full subcategory of module about this vertex algebra, which is the same as smooth, the category of smooth G hat module of level K. And yeah, sometimes this category becomes very interesting. And so in this case, associative variety, because the functor of taking the seats algebra is a right exact functor. So this is a subvariety of the variety for the universal one, which is the G star. And this is G invariant and conic Poisson subvariety. You just take a filtration. I forgot. G star times. So yeah.
So one of them is the G equivariance, and the other one is where you live.
So you consider as a Poisson category of a Poisson modules of G star, and this is the same as the coherent CFS on G. Yeah, so so this variety is so for generic K, this variety is just G star, because in this case induced representation is already simple. But there's another extreme when this variety becomes 0, consists of 1 point, and this happens if and only if K, this one is integrable. And this happens if and only if K is a non-negative integer. But so this is the most well-known cases, but certainly there are some cases between them. And as this law explains, there's certain category of affine Kac-Moody algebra called admissible representation, which is a full subcategory of category O of G hat, which have the same property as integrable representation. So this category is completely reducible. And also satisfies a modular invariance property, in the sense that the character satisfies the S2G invariant property. And it's natural to ask what kind of associative variety this representation have. And the theorem states that the associative variety of admissive representation is contained in the nilpotent cone. And in fact, it's a closure of some nilpotent orbit, which can be described explicitly. Now, I'd like to switch to double algebras. So you take some nilpotent element, and consider corresponding SL2 triple. And so from this data you can associate some vertex algebra called double algebra that Jethro talked about, which is defined by Drinfeld-Sokolov reduction associated with F, which it's realized by certain BRST cohomology. So this is a BRST cohomology, which is a version of just a version of the algebra cohomology associated with Drinfeld-Sokolov reduction. And so this is a double algebra associated with G at level K. And for this vertex algebra, we have the following diagram. So the algebra of this one is finite double algebra. Yes?
This term here, the set variety is this closure of this orbit.
Yeah.
So you're defining the set variety as the maximal spectrum.
Maximum, yeah.
Do you know what is the spectrum of the C2 algebra in that case? I mean, can you describe it as a sort of orbit, nilpotent orbit as well?
You mean as a scheme?
Yeah.
No, I don't know. It's non-reduced.
Already at the integral level.
Yeah, and except for a few cases, I don't have explicit description.
But okay, so I'll ask you then when you state the next thing.
So for this, yeah. So because a finite double algebra natural quantization of Schrodinger's slice, so you have this commutative diagram. This Schrodinger's slice. And so in particular, associated variety of double algebra is Schrodinger's slice, isomorphic, naturally isomorphic to the Schrodinger's slice. Now, so the nice thing about Drinfeld-Sokolov reduction is that it does not only define the double algebra itself, but it also defines a functor from the category of G hat module to the category of double algebra. So for example, you can restrict this functor to the category of Gaussian-Lustig full subcategory to see what happens. So you have this. So in general, double algebra is very difficult to describe. So we don't know how to. we don't know the commutation relation in general, but so you hope that you can describe the representation theory through this kind of functor. And in fact, this functor behaves quite well, meaning that the cohomology vanishing holds for any objects in this category, which means this functor is exact. So it defines a map between characters. And also, it behaves well for the associated variety. So the associated variety of the reduction is intersection of the associated variety associated variety of the V with S-Rho stress. So for any quotient. And this holds as schemes. This is what you wanted to ask.
Right, so it's surprising that you have these as schemes without knowing what they are.
It's a result of cohomology vanishing for the associated graded version.
What is this X?
X means so here I used as a scheme a spectrum of Zuz-Shitsu algebra. So I have more maybe Anne is going to explain in more detail about this. So maybe I don't say too much about this. So another example is if X a smooth algebraic variety, there's a notion of chiral differential operators on X, which was introduced by Marikov, Shetman, Weintraub, and Berison and Drinfeld independently. And so this object may not exist and may not be unique, but if it exists, you have the following diagram. So for the, as you can expect, so this is affinization of a usual differential operator on X. So you get usual differential operators as a result of this functor. And the you get push forward to of the cotangent boundary to X as a Poisson, as a C4 Poisson algebra. And you get the corresponding arc space version for the Poisson vertex algebra. And so this CDO for today's talk, I only need CDO for the algebraic group G, which has G as its Lie algebra. In this case, this CDO is very easy to describe. This is a one-parameter family of a vertex algebra. And this is just an induced module of G hat, induced from a function on on the on GT. So there's a natural action of the algebra to here, and you can induce. And you get certain G hat module, and you show that this has a natural structure of a vertex algebra. And so this corresponds to the fact that the global section of differential operators on G is a semi-direct product of UG and a function on G. So you replace this by G hat, and you replace by function on GT. And so this admits two commutative action. So there's a two commutating action of G on here from induced from a left invariant variant, left invariant vector field and a right invariant vector field. So there are commuting action, two commuting action of G hat, but at a different level. So you have a vertex algebra homomorphism embedding from here to here, the natural one, which send one to the identity function here. But also there's an embedding of vertex algebra for the dual level. So dual level, I mean k plus k star equals to minus 2 times h. This is known by both Gatsgori and Marikov and his collaborators. Anyway, so this is forgot to say. Actually, this holds for more general setting. So I should say this is for any vertex algebra object in Kazan-Lustig category. So meaning that the any so meaning vertex. This means that we have the vertex algebra homomorphism from here to here, and also V belongs to this category as a G hat module. So you can apply this theorem to CDO. So namely, you can do the Drinfeld-Sokolov reduction for CDO. And then corresponding associate variety is the intersection of the associate variety for CDO with Schrodinger's slice. But this is cotangent bundle to G with Schrodinger's slice. And because this is G times G star, so this is G times Schrodinger's slice. And this is what is called equivariant Schrodinger's slice by Rousseff. Slice. So this is a fine version of equivariant finite double algebra defined by Rousseff. And indeed, if you take those algebra, you get the equivariant equivariant finite double algebra. And this equivariant affine double algebra is quite useful in the sense that you can rewrite Drinfeld-Sokolov reduction using this vertex algebra. So namely, Drinfeld-Sokolov reduction is isomorphic to the semi-infinite, relative semi-infinite homology. With coefficient with m-tenth equivalent double algebra. So here you have level k modules. So for and here you consider as I forgot to say. So because I didn't touch on the right action of G hat, there's still action of G hat with level with the dual level. So you can consider diagonal action with respect to the right action, and so this sum of this level is minus 2 times HA. So you can take a BRST cohomology, and so this gives Drinfeld-Sokolov reduction. Maybe I state one more example. And as I said, you have still right action of G hat, and as a right action of G hat, this still belongs. This is still a vertex algebra object in casualist category. So you can take one more Drinfeld-Sokolov reduction. So maybe I just do principal reduction. So because this is the most interesting case. Then corresponding associative variety is associative variety of equivariant W algebra. Sorry. With intersection of this with Schroders slice. And but because this is G times S principal, so this is G times S principal. So this is what people call the universal centralizer. Which is isomorphic to equivariant homology on the affine Grassmannian for the dual group. So using Drinfeld-Sokolov reduction, you can obtain many interesting vertex algebra which affinize many interesting objects. So anyway, so I'd like to talk about main point. So one of in the title there's a word called Hicks Branch conjecture. So I'd like to talk about this first. And so the physicist Rastelli and his collaborators constructed a remarkable map which I denote by phi from the category of four-dimensional n equals to 2 superconformal field theories to the category of two-dimensional conformal field theory, which is the same as the category of vertex algebras. So they reduced dimension by 2, and which satisfies the following properties. So one of the property is that the central charge of the VOA, which I denote by C2D, is minus 12 of central charge for the four-dimensional theory. And what is more important is that the Schur index of 4D theory, so which is important observable or invariant, which is a Q series, is exactly the character of the corresponding vertex operator algebra. So you can compute this invariant using representation theory of vertex operators. And so quite this 4D theory is a quite rich theory. So this produces many interesting vertex operator algebras. So you want to know what kind of vertex operator algebra you get from this correspondence or functor, but you have this relation. The central charge is something which takes a value for unitary theory. So physics usually study unitary theory. So if you start with a unitary theory, you end up non-unitary theory. So what you get for this theory using this functor is not unitary. So something more exotic appear. So example of VOA coming from 4D. So let me so the main example of this paper considered is vertex operator algebra, a simple affine vertex algebra for G equals to E6, D4, E6, E7, E8, and K equals to minus HX over 6 minus 1. So this value is minus 2 here, minus 3, minus 4, and minus 6. So this is a negative integer level, which is quite unusual. But somehow you obtain this kind of vertex operator algebra. And there's another important invariant for this theory. Maybe I just erase here. So this has several important invariants. So one of the invariant is called so-called Hicks branch. So this is a hyperkähler varieties defined as a spectrum of the corresponding chiral ring. So this is certain geometric invariant of the 4D theory. Now, Moro and I studied these vertex algebras for different purpose, and found that the associated variety of this special vertex algebra at a negative level is isomorphic to the minimal nilpotent orbit closure of this corresponding Lie algebra. And it turned out this is exactly the Hicks branch of the corresponding theory. So this is some phi of t coming from 4D, and this Hicks branch is exactly the minimal nilpotent orbit closure. And in fact, this kind of correspondence holds for all examples for coming from for all non-example. And physicist believes now that this holds in general. So the conjecture says Hicks branch of 4D n equals 2 theory coincides with the associated variety of corresponding vertex algebra for any 4D n equals 2 super conformal field theory. So in other words, this diagram commutes. So here you take corresponding associated variety. No, yes, it's one of the point. This associated variety is not reduced, but Hicks branch is reduced. So
the ring doesn't have an importance, right?
No. So it's on the conjecture is only for the varieties. So this is a surprising conjecture for me because the vertex algebra is purely algebraic object, and it captures many interesting geometric structure. So I forgot to say that this Hicks branch is closely connected to the so-called is a Coulomb branch of the 3D gauge theory by 3D 4D duality, which are recently defined mathematically by Bravem and Finkelberg and Nakajima. But of course, not of course, but 4D theory is not really mathematically defined. So this Hicks branch conjecture is really a physical conjecture, not mathematical conjecture. But there are cases when everything is mathematical, which I want to going to talk about. So there's a distinct class of 4D n equals to super conformal field theories called the theory of classes discovered by Guyot, and S stands for 6. So this theory even comes from even higher dimension, the 6th dimensional theory. And so this theory is parameterized by Riemann surface, a pointed Riemann surface, and a semi-simple group Z. So this theory is denoted by SG, S sigma G. So this is pointed Riemann surface. And this is a flavor symmetry group. So this is a semi-simple group. And for the theory of classes, this Hicks branch described by Mowa-Tachikawa conjecture, which is a mathematical conjecture, conjecture on the existence of a symplectic variety, existence of 2D TQFT with targets in symplectic varieties, which is recently proved by Bravem, Finkelberg, and Nakajima. So so I forget hyperkähler structure and consider the varieties, a symplectic variety. Anyway, so this correspond is now mathematical, mathematically defined correspondence. And so corresponding VOA are some special class of VOAs, and it's called they are called chiral algebras of classes. So for each pointed Riemann surface and semisimple group G, you should be able to associate with certain vertex operator algebra. And so this is you can consider this a special case of recent construction of Fagin and Gukov, which associate with any 4D manifold to associate vertex algebra to 4D manifold. And for corresponding 4D manifold is just a this Riemann surface and the P1. So anyway, so the question is now whether you have this kind of commutative diagram here. So the question is whether we can upgrade I didn't explain more tactical conjecture yet, but upgrade more tactical conjecture to the setting of vertex operator algebra, and it was indeed conjectured that one can, it's possible. So now I want to describe this functor. So for this, I use because this is something to do with 2D QFT. We consider the category of two Bodhisms. So objects of here is a compact oriented manifold. So this is just disjoint union of S1s. So this is joint union S1s. Of circles. And I need another category, which is a target of TD to TQFT. So in this case, this is going to be a category of vertex algebra. But although I call this a category of vertex algebra, objects are not vertex algebra, but this objects are complex semi-simple groups. So this corresponds to this group. And morphism so I just draw diagram. So this is a morphism from 1S1 to 2S1s. And so in the relation with this Hicks branch, this corresponds to the Riemann surface with 3 points. So for each pointed Riemann surface, you consider 2 Bodhisms with same genus, and the number which has same number of boundaries. Number of boundaries is the same as the number of points. And the home here, so this one should be home from G1 G1 to to 2 groups, and this is a vertex algebra object in characteristic category at critical level. up to isomorphism. So the morphism are given by vertex operator algebra, which admits two commuting action of G1 hat and G2 hat, which are compatible with vertex algebra structure. So G1 is of course real algebra of G1, and G2. G2 is a real algebra of G2. and composition. So composition in the category of two-bodism is easy. It's already explained yesterday. So this is just this. And for vertex algebras, so we have V1 and V2. And then you define the composition as relative semi-infinite cohomology with coefficient in V1 tensor V2. So both has the action of G2 hat, so you consider the diagonal action. And because it's critical level, so the sum of level is minus 2 times critical level, 2 times critical level. So you can do the reduction. And I should say identity morphism from S1 to S1 here is just a cylinder. The corresponding morphism here is the CDO at a critical level. You can check that this is identity morphism from G to G in this sense. Yeah. Now the theorem states this is conjectured by Rastelli in a slightly different, in a physical language. So for each semi-simple group G, I forgot to say this category is monoidal category. The tensor product of group is just the direct product, and tensor product of vertex algebra are just usual tensor product. And this is monoidal category in the usual way. And there exists a monoidal functor from the category of two-bodism to the category of vertex operator algebra I just defined, such that the first, this functor should send a circle to the given this group G, and has to send identity morphism to the identity morphism. So it has to send cylinder to CDO. And third, so this is a real condition. This is somehow trivial condition. It has to send the cap to the Donifield-Sokolov reduction. Of CDO, which I called equivariant W algebra. So this three condition uniquely statement is that this three condition uniquely define a functor, and chiral algebra classes exactly those VOA coming from as an image of various two-bodisms. So if you want to find this kind of image of this theory, you consider two-bodism which have the same genus and the number of the one which have the same number of boundary as the same number of points, and the image is a chiral algebra, the corresponding chiral algebra classes. And moreover, sorry? This one, pair of pants? You mean, so this should be the same as? Hmm? You mean just this one? Yes, I'll explain in a minute. And moreover, you can define functor from here to here by taking associated variety, and this recovers the functor constructed by Bravero and Finkelberg and Nakajima. So in this case, this functor really commutes. So this is a statement for the Hicks branch conjecture for the classes theory. So maybe I should explain construction. Maybe I should explain why it's unique and then explain construction. So by axiom, composition like this. Because any two-Baudism is written as a composition of this and this and the punch, it's enough to construct the image of punch and check compatibility. So the problem is how to construct the image of punch. And but the image of punch, if you compose this with this, then this is the same as a composition of image of punch with the image of a cap. And this is just a cylinder. So this is a CDO. And this is, on the other hand, the right-hand side is, by definition, biaristic homology of punch with image of cap, which is equivalent double algebra at critical level. And as I explained, this is the same as a Drinfeld-Sokolov reduction of image of punch. So we just have to construct. So if you want to know this one, you just have to construct the inverse functor to Drinfeld-Sokolov reduction. And I claim this is possible. So this is essentially proved by Frankel and Gatsgory in the work on geometric Lagrange. So you have the equivalence category as a category of category as a critical level with a category of modulo of the Fagin-Frenkel center supported on the regular OPA. So I don't have much time to explain. So this direction is the Drinfeld-Sokolov reduction. And I claim that the inverse direction is given by BRST cohomology with respect to the you tensor this one with equivariant double algebra associated with principal nilpotent element as a critical level. And you consider the diagonal action of the Fagin-Frenkel center. And you view it as a D-algebra action because it's a commutative. So you can take a BRST cohomology. And but you have action with G hat. So this gives a functor from here to here, and I claim this gives an inverse functor. So the conclusion is that the image of punch the conclusion is that the more generally, if you have a genus zero Bordism with n boundaries, this can be described in terms of BRST cohomology with so I just write the W n minus 1. So W is image of cap. So starting from image of cap, which is a equivariant double algebra, you can recover the more general Bordism, image of Bordism, by taking a BRST cohomology. Does this answer your question? Yeah, stop here. Yeah, yeah.
So do you know what the associated variety of that one is?
I don't know.
I mean, your theorem holds, there is still an intersection.
Right, yeah. Yeah, I haven't thought about it. Yeah.